Alright, so a vector field over a plane region R is a function capital F that assigns a vector capital F of xy to each point in R. And a vector field over a solid region Q in space is a function F that assigns a vector in 3 dimensions to each point in Q. And so, if it's a vector in the plane, then it's going to be in 2 dimensions. Vector in a field, it's going to be in 3 dimensions. One example of a vector field that uses this example that we've covered would be a gradient. So in 2 dimensions, like the gradient of f of x, y, you know, we've went over all kinds of gradients. I'm just going to throw one out there. Something like this: 2xy plus 3y cubed I plus x squared plus 9xy squared j. That would be a vector field in 2 dimensions. And then that would be in the plane. And then in the space, you would just add one more dimension. So an example in 3 dimensions. And again, this isn't, I'm just coming up with random, say we had some gradient that gave us 2xi plus 2yj plus 2zk. That would be an example of a vector field in space. In general, this function here, or even in 2 dimensions, that's our capital F. That's how we define that. We can think of the parts as m of x, y, z times I plus n of x, y, z times j plus p of x, y, z times k. What does that kind of look like? You've seen some of this notation before, or something similar, but not in this class. Man, this DE final is going to be crazy, isn't it? Remember m of xy and n of xy? When we would have to, that was separable differential equations. And we use this notation because some of the stuff that we're going to do in here eventually in this chapter, we have to do some differential equation type stuff.
We don't have to take the final vote besides the grade.
As long as you can take your grade, say it times 3 and add a 0 to it and divide by 4, if you're happy with that, then you don't have to take the final. I really wish that I could do something for that, but I have to give comprehensive final. It just wouldn't be right. So this vector field is continuous at a point if and only if m, n, and p are continuous at that point. So whatever functions those are must be continuous to make the vector field continuous. The most common physical examples of vector fields are velocity fields, gravitational fields, electric force fields. Well, I mean, if you were going into any type of aerospace, anything, you're taking any aerospace engineering classes, or even electrical engineering classes, whenever you start dealing with electromagnetic fields and all that, I mean, this is just the very tip of the iceberg. But yeah, this is the basis for what you would learn about gravity, electrical fields, things like that.
How close have we gotten to like manipulating these fluids?
I don't know. Not sure. All right, so an electrical force field has the same form as a gravitational field. Such a force field is called an inverse square field. And so our formula for an inverse square field, f of x, y, z is equal to k over the magnitude of r squared times u, where r of t is equal to x of t I plus y of t j plus z of t k. And of course, you know what u is, right? What does u stand for usually? That's going to be the unit vector in the direction of r. So that's r divided by the magnitude of r. Alright, so there's an inverse square field. Now, how would we actually sketch a vector field? Let's look at a sketch of one, or let's make a sketch of one. Let's say that I wanted to sketch f of xy equals negative yi plus xj. So I mean, you can see this is probably about one of the simplest type of fields that you could have. It's not very complex there. So if we plug in a point, then we can get out a vector. The easiest points to plug in would be probably some points where one of them is 0 and one of them is a constant. So the easiest points to graph would probably be like 0, 1, 1, 0, negative 1, 0, and 0. I think I wrote 1, 0. That's supposed to be 0, 1. And how about 0, negative 1? So that's probably the easiest ones to graph, just because you just plug in an x and a y. Like, plug in this for your x, plug in this for your y, and then see what you get out. For each one of these, if I plugged in 1, 0, I would get just j. If I plug in 0, 1, I get negative I. If I plug in negative 1, 0, I get negative j. And if I plug in 0, negative 1, I get just I. Alright, so how would those look? So I'd have to be at the points. So I'm going to mark off a couple of points here, a couple of points here, a couple of points here. So at 1, 0, the magnitude would be, we could figure out the magnitude at each point. But I mean, we're not going to be exact or anything. Just really want the direction. So let's look at 1, 0. How would I draw an arrow in the j direction? That's what? Up. And then what about What about 0, 1? How do I go in the negative I direction? What would that be? To the left. And then negative 1, 0. Negative J directions down. And then 0, negative 1, I directions to the right. Now you could spice things up a little bit and maybe go to like 1, 1, but do you remember how to draw those vectors? If you have like an I and a J, you have to then you're going to have to do things like if you have two vectors coming from one point, then you have to draw the mirror of it there, and then so it's the one in between or whatever. The main things that I want you to know is that from any place where say an X is 0 or Y is 0, you can draw a vector field. We could go out here at 2, 0. Of course, the length would be a little longer, but it would go in the same direction, right? 2, 0, square root of 2 long, whatever that is, right? Because if it's 2 on the X, the square root and 0 there, the magnitude would be the square root of, maybe that would be the square root of 4 though, which is 2, so I guess it would be 2 units long. Up here it would look like that. Over here it would look like that. Over here it would look like that. Yeah, that's not really what I was going for, but yeah. If we were to graph this thing at some other points and do the type of graphing that you have to do, it would look something like this. Like what I was talking about over here. So say this looks like about the point. I don't even know what that is, but I'm pretty sure that you have two components, and so then you have to do it like this, and you have to graph between the two. It's just been so long since I've done those types of graphs, but yeah, it's not anything too complicated. But I'll probably get you to graph one like that. And so what I would always do is plug in zeros. X, either let X or Y be 0, and then the other one can be anything on that axis, and you're going to get some pretty graph like that. Look at this vector field. So any point here, see, whenever they found they were finding the magnitude of f, they found that it was an ellipse equation, and so all of these at different points or whatever would be an ellipse over and over and over. Definitely good to use the computer algebra systems, the CAS systems, if you have those to graph stuff like that. But it's kind of neat how you can sketch a vector field. And you just plug in the x's and the y's. Alright, one aspect of a vector field that we are concerned with is we want to, or we can figure out if a vector field is a conservative vector field. Alright, a conservative vector field is a vector field when there exists a differentiable function f such that capital F is equal to del F. So if there is some function that you can find the gradient of and get capital F, then it's called a conservative vector field. The function f, lowercase f, is called the potential function for capital F. Here's a little fun fact, every inverse square field is conservative. Many vector fields, including gravitational fields and electrical force fields, are conservative. Most of the terminology in this chapter is terminology that you would probably hear in physics. Alright, for example, the term conservative is derived from the classic physics law regarding conservation of energy. Everybody knows what that means, right? Or what that says. This law states that the sum of the kinetic energy and the potential energy of a particle moving in a conservative force field is constant. The kinetic energy of a particle is the energy due to its motion, and the potential energy is the energy due to its position in the force field. Okay. Next we're going to go over a theorem that gives the necessary and sufficient condition for a vector field in a plane to be conservative. So here's the test for conservative vector field in a plane. Let capital M and capital N have continuous first partial derivatives. On an open disk R. That confuses you, don't worry. On an open disk R. The vector field capital F of xy equals mi plus nj is conservative. So here's the actual test. If and only if partial derivative of n with respect to x is equal to the partial derivative of m with respect to y. Have we seen something like that? I have, in differential equations. Alright, that was how you could tell if a differential equation was separable. If the mixed partials were equal. Okay, so that's how we can also tell if a vector field is conservative in the plane. So are the following vector fields conservative? So f of xy equals x squared yi plus xyj. And here's another one. Alright, so how can we tell if they're conservative? Do you remember which is m and which is n? This is m, this is n. This is m, this is n. And so remember that if m is associated with I is x, right? I is related to x. They're double first cousins. That's the direction of x. So remember, you want to do the opposite. So we want to do the partial of m with respect to y. So that would be what? X squared. And we do the partial of n with respect to x. So that would be y. So the field is not conservative. Right? They're not equal, so it's not conservative. Let's look at this one. The partial of m with respect to y is 0. The partial of n with respect to x is 0. So what does that mean? So the field is conservative. Now, how can we find a potential function for a given field? So let's say that capital F of xy was equal to 2xyi plus x squared minus y j. Remember, del F is equal to capital F. Del F is equal to capital F. The formula, do you remember the formula for del F? It is the partial of F with respect to x times I plus the partial of F with respect to y times j. So in our field here, the partial of f with respect to x is 2xy, and the partial of f with respect to y is x squared minus y. Now, I'm going to go through this using the methods that they use, but this is basically the same thing that we did when we were doing separable differential equations. We're going to integrate the m, and that's going to give us a function. Alright, so when we integrate, remember, when we integrate m or n, you can do either one, then that gives you the answer in a form that you would want. We take the derivative of that and go back to this form, and then we can figure out the part that's missing if there is a part. So in your book they don't call these m and n, but remember that's what these are. This is m, this is n. The way that I explain this in differential equations is that you have some function f of x here. From that function, if you were to take the partial with respect to x, you get m. If you take the partial with respect to y, you get n. And so what we're doing is we're going backwards here, which we have to do with respect to x, but we pick up the y part when we do that. We pick up some function of y. So then we take the derivative and go back this way, and then we can compare it to our n that we have in the problem and figure out what part of y we had, and then we can get our answer. So I don't remember, I mean, it's been a while since we did that in differential equations, but that's basically what we're doing. So in your book though, they're not using m's and n's for some reason at this part, which makes the most sense to do. Your m here is this. So that's what we're going to integrate. We're going to integrate 2xy with respect to x. So this goes back to the answer or the original problem, or the original. This is going to be a form of our potential function. So that's going to be x squared y, but then here's the part of y that we pick up, the g of y, right? Because we don't know, whenever we integrate this with respect to x, this is the constant function y. We don't know what this is. To figure out what this is, you now take this answer and do what? Differentiate with respect to x. That's how we did that, or with respect to y. That's how we did that in DE. In Cal 4, the way that this is explained in your book, they integrate the m and get this. Then they integrate the n, whatever's in front of your j, with respect to y. So x squared minus y, they integrate that with respect to y. This isn't how we did it in DE, but it's okay. There's more than one ways to do things. But if we integrate that with respect to y, then we're going to have what? Some function of what? X. Right? Just like you pick up a function of y when you integrate x, you pick up a function of x if you integrate y. So if you do that, then you can tell that the function of y is equal to negative y squared over 2. The function of x, is there anything there? It's just going to be equal to k. Alright, so if you go back now to either form here, the only thing that you have to add in would be a k. So your potential function f of xy is equal to x squared y minus y squared over 2 plus k. If you do that using the methods that we learned from differential equations, the only thing different is you'll have plus c at the end. Okay.